avocado.
Okay, maybe I'm gonna be gone next year on this day.
Caleb, if you were gone this year, I'm saying hi to you now. Also, I love you, Nick.
Okay.
Hi, Anthony. Hi, Shannon.
This is weird. All right.
Grab a bit of that.
Suppose this is good review because you're gonna take a test that has all the calculus on it. Suppose we have the region bounded by x equals 0, x equals pi over 2, y equals cosine of x, and I want to rotate around the y-axis.
Well, you'll have to use the shell method.
Why do we have to use the shell method?
Because the axis of rotation is perpendicular.
We're on the y-axis, and we can't really like change that to something involving y's instead of x's, right?
We could attempt and then fail miserably.
I mean, it would be like inverse cosine in
equals
terms of y.
999 x minus 502.
Okay, so Joe says shell method. What would our radius be?
X
The height of our shells?
cosine of
All right, well, without a calculator, how are you going to do that? Without a calculator, we do not have the tools to find this integral. If that was like cosine of x squared, we could use u substitution. But we have x times cosine of x.
Oh,
Okay.
no.
That's great.
So, that stinks.
Yeah, I guess we just can't do it. It was a great calculus class, guys.
All right.
Tomorrow.
So I am going to show you how we get the technique of integration by parts, and then I'll show you how to use it. Okay? So let's start out with a differentiable product. And we're differentiable by the variable x. Okay? So if we were to take this derivative with respect to x, the derivative of y is okay. Going back to here, let me point this out. X cosine of x is a product that we can't use u substitution for. That's why I'm focusing on this product right here. Okay? Derivative of a product rule.
U prime.
Okay, so u prime times v
Plus U times V prime.
plus u. Okay. All right, you remember those days of differentials? Okay. We're going to write this as differentials.
Dude, my ideas might use this.
I know, I don't know why we pick u's and v's, but
Just
So
to
we
spite
can get
us.
all the Morlocks out of this.
What?
Morlocks from Time Machine.
okay.
They hated the sun.
Okay.
I don't know.
H.G. Wells' Time Machine.
Okay, so now since we have this written as differentials, I'm going to write them as integrals.
Oh.
That's fancy.
Right? It is. Okay.
Can you even integrate if it's like u times vb?
Well, that's what I'm going to show you. Okay. No. Here's. Can you give me like 1 minute, and then I'll tell you what we're going to do with that.
I got you.
Okay. So now I'm going to rearrange this. I am going to leave u dv on the right side, but I'm going to write it on the left. Okay. And then I'm going to leave the integral of dy and then subtract over the integral of v du. So I moved v du over here with dy, and then I used the reflexive property to write it backwards.
Oh boy.
Does that make sense? I'm just trying to say this doesn't Okay. The integral of dy.
Not a fan.
Do you remember seeing?
Wait a second. How did you get that?
How did I get the integral of dy to be what? how we integrate by parts.
Is this an improvement? I'm not really sure.
Here's the deal.
Gain some stuff. I don't
If
know.
we have a product to where we cannot use U substitution with, we can identify our U and dV and be able to figure out everything on the right side. If we know U, we can take the derivative for du. If we know dV, we can integrate backwards to figure out what v is.
So it's like taking like it's okay.
Okay, so it's integration by parts. So we take two parts of our original integral and we find the pieces that we need to put here.
Does it only work with
Well, I think I
molecules?
already know.
Heck, to be honest.
So technically you could make anything a product. So I'm going to say yes, but there's going to be specific cases that we can use it and specific cases that we can't.
So like I'm saying like if it was like a quotient rule or something, would you be able to do it or
But isn't a quotient just
No.
like a product out of it backwards?
Right. And it's not going to give us a solution every single time we see a product. Okay? Like if we have x cosine of x squared, it's not going to help us there, but U substitution will help us there. Okay? It's going to be for times where we can put all of these pieces together. Okay? So let's just talk through our example from before so I can show you what we would be able to identify. Okay? So every time you go to do integration by parts, from your original integral, you're picking out a u and you're picking out a dv. Okay? And that should complete your integral.
Well, I think U should be X and dV should be cosine.
I would agree with that. Joe, can you tell me why you would want that?
Because if dV was X, then you have to get a 1/2 X squared in there, and then you have to deal with fractions. Whereas if dV is cosine, then it just becomes sine.
Okay.
And it would be like X.
It's
sine
an easier integral to work with, is
Yeah.
kind of what you're saying. Okay? My suggestion to you is going to be, if there's anything polynomial, make that your u. Okay? If there's anything polynomial, make that your u. So, let's talk about integration by parts. I'm going to write it back up here. The integral of u dv is u times v minus the integral of v du. So we're going to need to know u, v, and du. Okay, well we know u. How do we find du?
You take the derivative.
Which is?
1.
Okay. If dv is cosine of x dx, then v would be sine of x. Okay. So what happens, our integral of x cosine of x becomes u times v minus the integral of v du. U was x, dv was sine of x. Excuse me, v was sine of x. Minus the integral, v was sine of x, du was 1 dx. Gabe, what's the integral of sine of x dx? Negative cosine. So what we have here is x sine of x minus a negative cosine of x plus c. Oh my. I don't know what just happened.
From 0 to pi.
Oh yes. I changed it into a
indefinite.
Oh, well, it's fine. We're fine.
You're fine with that?
Like,
I
You're
yeah,
fine with
at the end of the day, you could.
Yeah.
Okay. Should we practice again?
Yes.
Okay.
I would
I
agree
think that
with
would be a good
that.
idea.
I think it's either guys.
It's pi over 2 minus 1,
Thank you, Jen.
I think. You integrate it.
Oh, that's fine. I guess you would, that's true.
Okay, have a conversation at your pod. What should we make U? What should we make DV?
What should be U? I think E should be DV because not equal areas.
All right, Annalie, what do you think about U?
I know.
Okay, which means DV would be e to the x dx. Do you agree with Annalie?
Yeah.
Okay, let me tell you, if you tried to do it the other way, in the integral that you would need to subtract, you would instead have 1/2 x squared e to the x dx, and that would not be something you'd be able to do. So if you accidentally identified them the wrong way, you would get to a point where you can't integrate without using integration by parts and
Oh, rabbit
Can you
hole.
just get stuck in a loop
Rabbit
of integration
hole.
by parts forever?
Yes.
Oh, I
Until you
don't-
get it right.
Yes.
Until you guess one
Okay.
right.
Now we will look at one where that does happen
No matter what.
efficiently, yes, but it turns out to be okay. All right, so if U is x, du is 1 dx, and if dv is e to the x dx, then v is,
Yeah.
oh, that's lovely, isn't it?
I just think of the Spider-Man with like EDX.
It's x e to the x minus e to the
Well, it's x e to the x minus the integral, well, yeah, you're right.
Plus c.
The integral of e to the is e to the
Okay, so let's talk through this.
Oh,
We have
plus
u times v minus the integral of v du. U times v minus the integral of v du. Okay. You know what my kids last year called this? They called this voodoo.
Makes sense. Voodoo.
Yeah.
VU minus D.
It's more like move.
Yes, they decided to call it voodoo. And they called u substitution voodoo. So it was voodoo or voodoo.
Oops, dude. Oops, dude. It's just oof.
All right, here's a fun one.
Natural law.
We have not been able to take the integral of the natural log until today.
No, not today.
Is that a smiley face?
Yeah,
I
because it's
don't
an
know.
important example.
See,
See, that's how we used to do emojis back when emojis weren't a thing.
What's
Emojis
that?
now are actually just two
Yeah.
colons.
They got an
and those
emoji to
text.
describe my entire feelings.
Did you hear about the iOS update with 77 new emojis?
No.
Yeah, that was actually front page news.
See, and like winky face was this.
What is this sorcery?
I remember all of this.
I
used to-
I mean, now you should really be gone next year.
When you
Okay,
forget your letters,
so here's the
it's
deal.
like-
What is our only choice for the natural log?
Well, I'm
Make it
assuming
you.
what we're talking about today is integration
Make it
by
you.
parts, so.
Well, we're right. But if we're going to use integration by parts, do we want the natural log of x to be our u or our dv?
You.
Okay. We don't know how to integrate natural log, so we don't want to integrate natural log, right? So you to be our natural log, which means we're multiplying by 1 dx. So we would identify u to be the natural log of x, dv to be dx. Okay, how does this help us? Well, what's the derivative of the natural log?
1 over x. Oh no.
And v would end up being okay. That was kind of a strange moment there.
You always wait for someone else to say it.
So we have u times v, which is x natural log of x, minus the integral of v du.
Wait.
Which is?
X natural log of x minus x plus
Okay,
c.
so x times 1 over x is 1, so we essentially have the integral of dx. So we have x natural log of x minus x plus c.
It's not as ugly as I imagined it.
I like it.
Isn't integration by parts fantastic?
Just memorize that one.
I know the integral of the natural log.
Can we walk on over to Calc BC and be like, guess what, Prue? We can do math that you've never even dreamed of. Just to flex.
Okay, so I have to tell you a funny story. I had a student in my 7th hour pre-calculus class ask me, is AP Calculus AB limited, or like what's the difference? And I was like, haha, that's funny. And I like walked away.
Oh.
But he was really asking a question. And I was like, oh, sorry.
What do you mean? What did they mean?
Because we were like learning about limits, and so I thought that maybe he had
Wait, in
like.
pre-calc?
Yeah.
What about limits in pre-calc?
No, like my AP
Apparently-
class was.
Oh.
Did you guys do
So-
limits at the end of last year in pre-calc though? Because like everybody, no, not at all. Really? What they knew that they were talking about. I was like confused.
Okay,
And again.
And again.
You know what?
just write down the example.
I think we can do this.
Darby, your optimism will get
Okay, now I do want you to notice that there is a polynomial and a power less.
But it's the wrong.
It's the wrong way, right? If we were e to the x squared times x, it would be perfect because we could use e substitution. However, the x squared is being multiplied to the e to the x, okay? So it's not helpful.
No.
So we would have to make u equal,
X squared.
and dv would be e to the x dx. Okay? Well, this means du is 2x dx, and v is e to the x. Okay. So, our integral, we have u times v minus the integral of v du.
Oh, are we gonna have to do it again?
Well,
Well, it does say and again.
yeah, it does say and again.
Again,
Okay, why does it need to be and again?
We have to do it twice.
Because now we have this guy right here. Okay, all right, so second time around. Do you mind if I throw the 2 on the outside, or
Please
do
throw
you
the two
want?
on the outside.
You do? Or
Yes.
do you want to keep it?
On the outside. Wait.
Because I'm
Okay.
confused. Keep.
Let's keep it. Let's keep it. Sorry, I'm gonna overrule you, Darby.
It's okay.
Okay.
No, I just wrote it down. Don't do the.
So u we would make 2x. dv we would need to make e to the x dx. Okay. Well, that would make du 2dx and v e to the x. Okay. So now what we're working with
Is parentheses in this? No, it's just subtraction.
Yeah.
well, it's subtraction, so yeah.
Really? Oh yeah.
So we would have x squared e to the x from before minus our integration by parts u2 times v2 minus the integral of v du.
Yeah, I can do that.
Oh, whoops, I had space for it.
now. What?
Come on, tell me you're not feeling the same.
Are you feeling it now?
Are you not feeling that was not?
Wait.
It's a lot of
Work.
It's just pressure to distribute.
Oh, it actually says that.
Yeah, that's what I was
Yeah, it's a
referring
shame you
to.
can't
Okay,
factor any of that.
what if I told you?
No, not the triple.
What
Don't
if-
hit me
No.
with the triple.
I'm not prepared
Patience.
for the womp
Patience.
of
What if I told you there was another way that we could do this?
Did I say yes?
I-
Like, it would still be integration by parts,
Would it be
but
more
when
fun?
we have to do it multiple times, we have what's called a tabular method that could help us.
Ooh.
Okay, so let's talk about a pattern here, right? Let's talk about a pattern.
I see 0 patterns.
We took the derivative of x squared to get 2x dx. And then what did we do? We took the derivative of 2x to get 2 dx.
Oh.
Right? We took e to the x and we integrated it. And then we took e to the x again to integrate.
For example, because e to the x is the same. Like it's giving us a false pattern.
Okay? Not every example can be done this way, but if there is a polynomial especially, and you're going to have to do integration by parts more than once, we can do what's called the tabular method. Okay? We can make a column for our differentiate piece. We can make a column for our
Integrate?
integrate piece. Okay? Now, the only thing is we're going to have to be careful with a couple things. First thing is, we subtract when we do integration by parts, so we have to account for subtracting and then subtracting and then subtracting, right? So first thing we're going to do, we're going to choose our u and our dv, right? What's our u? So that goes in your d column. Our dv goes in your integrate column. Okay? You need to take the derivative of this guy until you get to 0.
Okay.
So help me.
2x.
And then,
2.
and then.
0.
I could do the other side.
Then you need to integrate the other side.
Oh, that's gonna be so difficult. I don't know if I can do that.
Oh wait, we never get to 0.
Okay? Now, we do have to account for that subtraction. So you're going to go to this differentiate column, and you're going to say plus, minus, until you run out.
Wait, is that -0 I see there?
So you pretty much only have this 0 because we need this e to the x right here. What happens is we pair up diagonally. Right? Because we choose u and we pair it up with v. Well, this is v because we integrated. And then we take our next u and we pair it up with v. Well, this would be our next u and this would be our next v, etc. Okay? So what we get is positive x squared times e to the x, negative 2x times e to the x, positive 2 times e to the x, and we run out like we're at the end of this column, plus c.
I'm gonna do that.
Yes.
Why don't they just call the columns u and v?
Because technically we don't start out with u and v.
You start with u. Then why not u and dv?
If you'd like to call them that, you may.
Well, then I would.
Look at the D and I because it tells you what to do with them.
Yes.
Well, maybe you want to write both like Gabe did.
That's fancy.
Okay, you're one step ahead of the curve. I'm so
Make
sorry.
the U and the V the subscript.
That's what I say. Don't be like.
I'm gonna change this. This is x cubed sine of x dx.
Well, so
you
no,
literally
it's
made
not.
it such a.
Yes.
So is the like u or whatever the polynomial like say it's to the 2u, so you do it like to does the variable indicate like how many times you do it?
Yes. So this was x squared e to the x.
So you'd integrate by parts 2 times.
Yes. Which means like this one right here, if we did it like the normal way, we would have to do it 3 times. Okay.
And it's the last
But
example.
Okay, do we want to do that? I think I'd rather use the tabular method, right? Okay. Polynomial, we always want to differentiate because in this method we need to get that down to 0. Like that's the only way that this works. That's a cube.
I was slightly concerned.
Okay, so when we differentiate that column, 3x squared, 6x, 6, 0. So now we need to integrate that same number of times. Okay, that's why we go all the way down to the 0. So we don't really need it, but we need to know how many times to integrate. So the integral of sine of x, negative cosine of x,
Negative sine of x.
negative sine of x,
Cosine of x.
and cosine of x.
Sine of x.
Okay. Don't forget to alternate your signs here.
So it's negative x cubed cosine of x plus 3x squared sine of x plus 6x cosine of x minus 6 sine of x plus c.
Yes.
Nice.
So negative x cubed cosine of x.
Oh, you that's true.
So we're multiplying, right? Oh no, I'm gonna have to go down here.
I'm vibing. I'm a supporter.
I enjoy this.
I like this better
Can
than
you
the
tell why this is one of my favorite things to do?
Well, the
Yes.
table is like the simplest
Sorry, we
part.
didn't ask
That's
you
really
to
fun
comment.
to get it to 0.
Okay, so this is just very basic integration by parts. What I'd like to do is have you master the basic setup of it, the basic tabular method. On Monday, we will look at some of those that like cycle, like what if we have e to the x times cosine of x? Both of those did,
That would get to 0.
yes, both of those derivatives and integrals cycle through. So how do we do that? Okay. We will also look at some different ways that I could ask an integration by parts question. Okay. But we have 8 minutes left in class. So open up your book and do at minimum. Well, I think give me your gold sheet here. Yeah. Do a minimum 2 to 3 problems.
First problem.
It should all be on that one page, Kaylee.
Let's do the recap.
It should all be on that one
Yeah.
page.
It's just open the chapter.
Oh, I was in the wrong book. I'm sorry.
I mean, we could probably do